All right, hello everyone. My name is Wu Jung. I'm a principal data scientist at Pivotal. And today we're going to be speaking about how to run our data science workloads in massively scalable data platforms like Greenplum database. To kick things off, I wanted to begin this session by kind of taking a bird's eye or a landscape view on the selection of open source machine learning models or tools that are purpose-built for large data sets. And so we have, MADlib, which is a Apache project that includes many popular libraries for machine learning to run on Greenplum database and Postgres. We also have H2O and SmartMLlib listed here. And then finally, we have a section in there for procedural language extensions to R, Python, and Java on the lower left-hand corner there. And that's actually what we're going to focus on for today's session. We're going to go into a lot of detail on procedural language R and how it can be parallelized on MPP platforms. Now, a guiding principle or a set of guiding principles when we're kind of speaking about data science tools for large data sets is that data scientists really want to, at the end of the day, be able to extract actionable insights from data. And we don't want to limit the size of data sets or scalabilities to be a concern for data scientists who just want to get in there, clean up the data set, prepare the data set, run some machine learning models, and then get to discovery. What we've often seen are data scientists, statisticians, kind of working off of their laptop machines or servers that are running R, Python, and SAS. And while that's great from a usability perspective, I think when we're thinking about data scalability for large data sets, there are huge bottlenecks. Number one, there would be a large amount of data movement between the data store and the computing environment. And then secondly, there are no guarantees that the computing environment, so your laptop computer, let's say, would be able to scale to the amounts of data that you are pushing and requiring for computation in that layer. On the other hand, a lot of data scientists, statisticians extract their data from databases, which run on pretty powerful hardware. And some databases like Greenplum are purpose-built for scalability, right? And so the notion here is to get your models closer to the source of where the data is stored, and do this more and more as data sizes grow, right? So I'm going to be speaking about how to parallelize procedural language R in this talk, but in many ways, you shouldn't be interested in what I'm going to talk about if all you're running are models on your laptop using smaller data sets, right? We don't recommend PLR or Greenplum for those types of workflows. What this talk is intended for are scenarios where you've run into the ceilings, where you've run into the roadblocks on your laptop and you're looking for more scalable solutions to get to faster insight. Now, kind of on that note, there are a lot of tools out there. Some of the tools that I've listed previously, including MADlib, MLlib, H2O, that are out there for doing just this, right? So data analysis on large data sets. And oftentimes, it's a bit of a challenge to kind of understand when to use what tool, right? And so this is kind of a mind map, if you will, of, I guess, how a data scientist here at Pivotal would select which tool to use, right? And as we'll see later on in the session, we're going to be focusing on just one pathway of this tree. But to kind of give you guys an overview, typically we like to prototype some data science model building in R, or maybe directly model in MADlib or Pivotal R, right? And once we're at a point in the development cycle where we have a pretty good idea of which algorithm we want to use for the final set of deployed models, we can then ask ourselves the question whether the algorithm of choice, let's say a decision tree, a random forest, if that's available in MADlib or Pivotal R as a module, right? If so, then our recommendation would be to go ahead and build those final set of models in MADlib or Pivotal R. But there are scenarios in which the answer to that question is no. Let's say you just read this really innovative academic paper by a leading statistician, and she publishes the results not only in the paper but also through an R package. And it just so happens that you also, for the problem at hand, it would make a lot of sense to kind of incorporate that newly found algorithm into your workflow. That's sort of the perfect scenario for something like procedural language R or procedural language Python. Oftentimes, a lot of the cutting edge research in machine learning, AI, statistics are usually accompanied by an R package or a Python package that practitioners can then use in their workflows, right? And so that's exactly I guess the workflow that we want to focus on for today's session, which is a scenario where the algorithm of choice isn't available in MATLib, Pivotal R, H2O, MLlib for that matter, and opportunities for what we call explicit parallelization exist, right? And in this specific kind of workflow, this is where we'd highly recommend building your final set of models in procedural language R or even procedural language Python. Again, in today's session, we're going to be focusing more on the R side of things, but a lot of what we're going to talk about for R can also be done on Python and Java. So before we get right to it, we kind of wanted to describe a little bit and kind of define what we mean by explicit parallelism or data parallelism. This is a scenario where little or no effort is required to kind of break up the problem at hand into a number of smaller parallel tasks, right? So those of you who are familiar with the R ecosystem, this is kind of akin to the apply family of functions in R. You can also think of it as a parallelized for loop. MapReduce also kind of follows this pattern of coding. I guess in plain English, one way to think about this is if you have everyone in the room kind of together, and like the mission is to count up a deck of cards for some crazy reason. And so you have one big deck, and you could, in one scenario, have one person in the room count up that entire deck by herself, which would take a certain period of time. In another scenario, you could divide up that deck into smaller chunks to everyone in the room, and have each person in the room count her stack, right? And then you can have that run in parallel and essentially kind of get to orders of magnitude improvement in the amount of time it takes to compute the card counting problem. And so that kind of applied to more, I guess, sophisticated machine learning routines would be the perfect scenario to make use of PLR. Now, to give you a background, so to take a step back, I mean, you guys are all probably familiar with what the R language is. It's a software package for statistical computing that has grown out of the original S language implementation, so it's the open source version of S. But procedural language R is actually something that was developed for the Postgres community by Joe Conway. And it allows Postgres users and Greenplum users it allows them to actually write R code and embed R code inside of SQL user-defined functions, right? Now, in the world of Postgres, this would be, I guess, not be parallelized. But although you'd still have R code embedded inside of SQL, but then it would be on a single node Postgres machine. What's interesting for PLR in the context of using it on Greenplum is that you can then parallelize it by the nature of Greenplum's MPP architecture, right? And so if we think of this diagram here as your Greenplum cluster, and you have a master node and then several segment nodes here at the bottom, you can have an R runtime that are running in parallel across the stack and increase the time it takes, increase I guess the productivity of your data scientists as they get to insights. Here's a very simple example, right? So let's say we have data for US states, and we have distributed on Greenplum by state. And so in segment 1, you'd have data for Tennessee. In segment 2, you'd have data for California. In segment 2, segment 3, you'd have data for New York, et cetera. What you could do with PLR is essentially build the model for Tennessee in the same node in which the Tennessee data lives, build a model for California in the same node in which the California data lives, and do this for all the states. And if you go through this workflow, the time it takes to run a model for one state would be the same amount of time it would take to run a model for all 50 states. Let's say if you have a 50-node cluster of Greenplum available, right? And so it's parsimonious in that it piggybacks off of Pivotal's parallel architecture. You're minimizing data movement because data by state stays within the segment. And it increases productivity because you're now building the predictive model for each state in parallel. And we're going to go through a couple of code examples, and rather than kind of show that through slides, I wanted to jump to a GitHub pages site that we've put together. And if you go to this link over here, so pivotalsoftware.github.io/GPR, and then you go to usage and best practices, we actually have a pretty good guide on how to get started with PLR on Greenplum database, right? And one of the first things that you should do when you're using PLR is to make a plan. And so as we say here in the body of the text, you want to ask yourself whether the problem that you're trying to solve can be phrased as an explicit parallelized problem, right? So for example, like, could we parallelize by state? Could we parallelize by ID? If you have something that you could break up your data into, then and you are okay with kind of building independent models by that group, then I think it's again a scenario where it would make a lot of sense to make use of PLR in that workflow. So the first thing that you need to do is actually prepare your data for use on PLR. And we do this very often by using the arrayag function in SQL, right? And so here's a very simple example. If we use the abalone data set, that's very popular. You can get understanding of, let's say, some example records of this data set here, let's say 3 records. We'll notice that there are not only quantitative data values in this data set, but then there's a categorical column called sex. And in this case, I think the 3 values that are available are M, F, and I. And so, one way you'd kind of parallelize this workflow is to array aggregate each variable of interest, group by the parallelization index. In this case, one suitable index would be the sex column. And then you could distribute your data by the parallelization index. And so to do that, you create a table called, let's say, abalone array, and you would kind of specify sex as one of the columns in your new table, and then arrayag all the other quantitative variables that you want to eventually include in your workflow by using this arrayag function. And then you notice here that we supply a group by sex clause here, which would essentially provide the grouping that we would need to run the PLR function and parallelize our models by the sex column.
Can you say that the GitHub URL again?
Yeah, the URL is pivotalsoftware.github.io/gp-r.
And I'm actually seeing one by Joe Conway for PLR.
Oh yeah. There's another one. I think it's, if you Google Joe Conway PLR, he has documentation on the Postgres, the original Postgres implementation of PLR here as well. Yeah.
So the Pivotal Labs one is a parallelized fork of Joe Conway's PLR?
The original PLR package, yep, for Postgres, yep. Mm-hmm.
And what is the maintenance we do between, because it looks like Joe Conway still maintains his implementation?
That's a good question. I don't know, Ivan, if you have any insight on how well we keep up to date with the latest.
It's pretty much just ported the same PLR, but to the MPP execution.
Okay.
Yeah. And so, if we jump back to the example here, we start, with arrayagging our data set by the grouping variable of interest. And then that gets the data ready. But now if we're in the context of creating a function that will create some return values, we also have to think about and kind of preempt what we actually want to get back from the PLR function, right? And so in the case of, let's say, a regression routine that we'd want to run on PLR, well, you'd get back the variable name, you'd get back coefficient estimates, you get back standard errors, you get back t-statistics, and you get back p-values, let's say, right? And so you kind of create this Postgres type or this skeleton table that sort of defines the structure of your return type. And in this example, we're going to call that structure LM abalone type. And it's essentially going to be the target table or the target skeleton in which you're going to feed our results or output set from PLR. Yeah. So at this point, we have prepared the input data for use in PLR, and we have laid the groundwork to be able to store the output from PLR into tables in Greenplum, right? The next section is now the actual definition of the PLR function itself, right? There are a couple of helpful rules to follow here. Each argument of the PLR function and its specified data type needs to correspond to a column that exists in the array aggregated table that was created in the data prep step. And so what I mean by that is each argument that you create in the PLR definition function, so S weight, rings, diameter in this example, has to correlate with a array agged column of data in your transform data set. So S weight, rings, and diameter in this example code over here. The second helpful rule here is that the return data type of the PLR function should be a set of the composite type that was created in the return type step. And so when you define your return values here in the function definition, make sure you include return set of LM abalone type so that the function behaves as intended. And so if we look at our function definition, everything inside of the double dollar signs are R code. So this is pretty much the same R code that you'd write on your R console if you were to do something like this on your laptop. But then we wrap it around kind of this SQL create function command, which again specifies the three arguments, the three inputs that need to be provided to this function. So in the context of linear regression, we'd have S weight here as the response variable, rings and diameter as the explanatory variables that we eventually want to incorporate into the function. And you'll notice here in the first line of the R code, that's exactly what we do. So LM is the R function for linear regression, and we're saying S weight is the response variable, rings is one of the explanatory variables, and diameter is the other explanatory variable. Yeah, Ivan.
Are you trying to predict the weight of the fish based on the other variables?
Yeah, like the weight of the abalone in this case based on rings and the diameter of the specimen. Yeah. It's a pretty contrived example, but the abalone data set is used for toy examples like this. And so, what we want to get back from this process are the coefficient estimates and their summary statistics. And so we specify that using the summary command in R, and we return kind of a data frame or a table that contains this information. You'll notice that here the final line of the function definition is language PLR, and so that tells Greenplum that, hey, everything in the double dollar signs is R code, and you need to now invoke PLR to be able to create and execute this function. So everything up to this point, we have, again, prepared the data, we have kind of set up, laid the groundwork to have Greenplum ready to receive the results from the PLR function, and we have now also defined the core process, the PLR function that is estimating linear regression on this abalone data set. We haven't actually run the model yet, and so that's the next part of this guide here, so PLR execution. And so to do this, it's pretty straightforward. It's a one-liner select statement. You say select sex, comma, and then you invoke the composite PLR function that was created up here, right? So LM abalone PLR, that's the same name as this guy up here, right? And the from clause has to be from abalone underscore array. Again, that's the post-transformed data set, array ag data set that we've created in this line of code, or these lines of code up here. And once we do that, we get back a plain and simple SQL table, SQL set of results that has sex, which is the grouping parameter, the variable name, and then corresponding regression summary statistics for each variable in the model that was estimated. So that's sort of like the, I guess, the hello world example for PLR. And I think through, in the rest of this session, what we're going to do is we're actually going to kind of expand on this idea and do some interesting, I guess, kind of interesting synopses of how we've creatively used this framework for more complex workflows on Greenplum database. Let's switch over back to PowerPoint here. And kind of, one way to do this is to make this a little bit more interesting. We talked about abalone in the GitHub Pages site, but now let's pretend that we're kind of analyzing census data, and you want to, predict a person's wage, as a function of whether or not this person rents a house and whether or not she's married, right? And so you'll see a lot of the same constructs as we saw on the GitHub page. You kind of just start by writing the R code as you would on your R console on your laptop. And then you create, again, kind of that return type that we're talking about, which is going to store the model results. In this case, it's identical to the previous example. So we're going to store the variable name, coefficient estimate, the standard error estimate, the t-statistics estimate, and the p-values from this workflow. And then we're going to kind of pop that line or lines of R code inside of our definition for the PLR function, which again has wage, rent, house, and married as the three arguments, the three variables that we'll eventually invoke in the R code here. And then we're going to return coefficient summary statistics at the end of this function. And we're going to execute it now. And again, this LM function is the same function that we've just described or defined in the previous slide. And here again, you get back a plain and simple table containing the variable names, the state, and corresponding regression summary statistics for each tuple. All right, so as I mentioned before, this is sort of what I've just described is kind of the bare nuts and bolts of sort of how you'd use a PLR function. I'm going to kind of go into ways in which we can apply this knowledge to real problems and use cases that we've encountered with our clients in consulting engagements. And so the first one here is something that we did for a utilities company. And what they wanted to do is actually detect anomalies in their smart meter readings. And so this utilities company had a smart grid of smart meters that were collecting data, I believe, at 5-minute intervals. And we had a couple of years worth of data for this smart meter data for one geography in which this utility was operating in. And the objective here was to build a framework for anomaly detection to leverage in revenue protection initiatives. And what we did was we made use of PLR functions, specifically fast Fourier transform and time series analysis functions in R that we invoked through PLR to identify 191,000 potentially anomalous meters in their geography. So this was about 7% of all the meters that they had data on. This was done on Pivotal Greenplum using PLR along with MATLib. And from a performance perspective, the FFT portion took only about 90 seconds to complete for over 3 million meters, right? Comprising about 3.5 billion meter readings. And then in the other portion of the analysis, which made use of ARIMA models, it only took about 36 minutes to compute ARIMA models for about 3.5 billion readings, so about 0.7 milliseconds, per meter. Now, to kind of give you all a little bit more of a background on how we went about doing this, we started with looking at all data from all meters, so 4.5 million meters from about 20 billion meter readings. And then we needed to do some filtering and data cleansing, which kind of had us land at about 3.1 million meters or 3.5 billion meter readings. The first thing we did was to run a fast Fourier transform analysis on the data to detect anomalies. And that identified about 500,000 anomalous meters or potentially anomalous meters in the network. and we kind of, presented this model back to our stakeholders at this particular company, and they wanted to see a further reduction of the false alarms, the false positives, right? And so what we did was we kind of came up with a workflow where we, in addition to the FFT analysis, we also ran an ARIMA model that identified a separate set of about 500,000 anomalous meter readings. And if a meter was flagged as anomalous by both the FFT analysis and also the ARIMA analysis, it made it into sort of that final list of meters that we asked the forensic team to go out and analyze, which substantially reduced the number of false alarm or the false positives that were produced by this workflow, right? So a very interesting use case. And in the context of this talk, I wanted to also show some PLR code that we use to actually go about and do this, right? And so as we saw before in the examples in the previous section, we started by creating a type to store the frequency spec and max frequency estimates that are coming out of, let's say, an FFT routine. We know in advance that these are the three types of things that we need to capture back from a fast Fourier transform routine, right? And so we kind of set the stage for that, and we create a SQL type as a skeleton target table. And then we create a PLR function to compute the periodogram and then return the frequency with the maximum spectral density back to Greenplum. And we do that by using the spec.pggram function in R. And again, everything that's in the $$ is just your plain and simple R code that you run on your laptop. And what we were doing here is we were returning the frequency value with the maximum spectral density. And that's kind of provided in these lines of code. And then lastly, we execute the function by invoking the pggram concise function pointing to a data set named meter_data. And if we execute this, then we're able to now essentially get back parallelized executions of the FFT algorithm grouped by geographical ID and meter ID. So essentially, for each meter that we're tracking in this data set, you'd be running an FFT in parallel inside of Greenplum. Yeah. And we get some really interesting results back by doing something like this. I won't go into too many details, but we found that most households use energy in daily or half daily cycles. And so if we go back to this PLR function, this frequency with maximum spectral density that we spoke of here, that's the thing that's being returned by the function. We plotted all those values, excuse me, on this graph here, and you can think of this one as a histogram. And so we're seeing that most households have a 24-hour cycle of energy usage, and cycles that, households that don't see a 24-hour cycle see a half daily cycle usage of energy. And so that's great, because this kind of tells us what is normal, right? And so every meter that kind of falls outside of this normal range can then be flagged as potentially anomalous meters, right? Which are about 20% of all the meters that were found in this analysis, right? And this is compelling because before running models like this that could potentially automate and increase the productivity of forensic analysts in identifying anomalous meters, I mean, let's compare this to what this person would have to do without these sorts of models, right? So in the before workflow, this person is looking through thousands and thousands of graphs like this, and then among the normal graphs, which look like kind of the ones up top here, this poor person has to kind of find out and flag the meters that are displaying this type of activity on the graph. And this is fine if it's just 2 pictures that they need to look at, but it's like thousands of pictures every single day that they would need to plow through. What a workflow that we've done, that we've described here in PLR, what that would enable is essentially kind of reducing the number of graphs that look like this and increasing the number of graphs that look like this that this forensic analyst would have to sift through in his or her workday, right? And so it really kind of allows smart decision support and kind of directing human resources to focus on specific problems that need their attention the most, right? And so we were really happy with this analysis. And again, it was a lot of it was done inside of sort of this PLR framework that we're covering in today's session. The next one here is something that we did for a major media company where they wanted to get a better handle on revenue forecast for the advertisements that they're selling in their publications. And so what they wanted to do is essentially come up with a revenue forecast model for every title that they were publishing in their portfolio. And again, real nice results and impact that we had on the business by increasing the accuracy of the revenue forecasts, and in turn giving their marketing team better insight on how to optimize their advertising portfolios. But here again, kind of for the purposes of this talk, I wanted to go straight into the PLR code that we wrote in this project, which did something very interesting. So up to this point, we sort of assumed that each PLR function would have the same exact model form. And then we kind of followed kind of a traditional coding structure as we're kind of invoking functions and grouping by parallelization parameters of interest. What we did here was allow for the variation of the types of models that could be run in parallel inside of Greenplum, right? So if you remember back to like our regression by state example, every single state was running the same regression model, right? It had the same model form. It was predicting wages as a function of whether or not this person rents a house and whether or not this person is married, right? And that same model has to be run on every single state, and you can't allow it to vary, at least in that framework. This extends that and allows it to be a little bit more flexible by essentially coming up with a metadata modeling table that we create beforehand. And this metadata modeling table, it actually contains strings of code that will then look up and invoke inside of PLR functions, right? And so what do I mean by that? Well, in this case, we're building a separate model for each magazine title, right? So for magazine 1, we'd want a model form that looks like this, which is different from the model form that we're expecting for magazine 2, which is again different from the model form that we'd want to run on the data for magazine 3. We do that for all magazines in our portfolio, let's say 25 magazines, and we essentially have potentially different models that we're running for every single magazine. In this case, we're running AutoArima for magazine 25 and just plain old vanilla ARIMA for magazine 3. But you could extend this concept and say, I want to run neural networks for magazine 25, decision trees for magazine 3, and random forest for magazine 1. And you essentially kind of pre-populate strings of code inside of a metadata modeling table, right? So that's sort of the first step in this analysis. And then what you do, well, this next part is similar to what we've done before. We're going to create the return type to store results from this modeling workflow. So in the context of revenue forecast, we want to know the month, the actual value of revenue, the predicted value of revenue, and lower and upper bounds for our forecast. And those are the things that we're going to return from these sets of models, right? Now what we're going to do next is create a PLR function to run parallel models by the publication name, right? And we do this by invoking the forecast library in R. I'm going to come back to this point because it's important. And then what we're going to do is we're actually going to read from that model metadata table so that we don't have to create this very messy set of R code in here where we're kind of saying, if magazine title is equal to 1, then invoke neural networks. If it's equal to 2, then invoke random forests. We're keeping this clean, and we're keeping it as a reusable set of code. And any tweaks that we make to the model, we're just updating this kind of model metadata table, and then running again that same exact PLR function, right? So what's happening here is that we are parsing, text parsing, what we've created here, which is just strings of code that we're storing inside of a table. We're parsing that inside of PLR, evaluating it, and then allowing each magazine title to have its own distinct and unique algorithm to run and estimate models on, right? Which is very powerful, again, in the context of being able to be very flexible in how you're parallelizing your workflows, right? I said I wanted to get back to this because For the R users over there, this is a huge deal, right? So what are we doing? We are invoking an add-on library inside of a PLR function. So there's over 5,000 libraries on CRAN that are available for download. And with PLR, you not only get core R functionality that comes with standalone R, but you can bring in any of the 5,000 libraries in CRAN and have them run in parallel in the same manner that we described in this session, which is very powerful in terms of being able to leverage algorithms from a wide range of different academic disciplines and different industry verticals, right? So I'm, in this case, invoking the forecast library, but you could invoke XGBoost if you want to run gradient boosting machines. You can invoke the JAGS library or the STAN library if you want to run some Bayesian regression routines. Really anything that's available on CRAN, anything that's available in R, you can then parallelize inside of PLR. And kind of using this workflow that I've just described, going back to this use case, we were then able to kind of come up with revenue forecasts for each magazine title. Not only to get the numerical summaries, obviously we've had to mask the actual numbers here, but then you can get to graphs that you can also generate in R in parallel, which is actually going to be a good segue into our next session, and have it also display the actual values in red, the predicted values in blue, upper and lower bounds of the forecast in light gray. Now, we've really kind of taken this concept of parallelizing R to the extreme here in the Pivotal Data Science team, because we said, hey, it's great that we're parallelizing models, but could we potentially parallelize visualization generation by using this workflow, right? We've made, I guess the industry as a whole has made lots of great strides in parallelizing and distributing machine learning routines, but it still has a long way to go in making visualization scalable, right? So a lot of tools like Tableau, although they're great for smaller data sets, it doesn't scale to large data, Plotting functions in R and Python are the same way. But again, kind of by using the data parallel approach, by breaking up your data into chunks and having visualizations run in parallel, you can then, again, increase the scalability of plots and visualizations in your data science workflow in the same way, right? And so here's sort of what I mean by that, right? This is something that we did for a major retail company. We created a PLR function that essentially made use of R's PDF function. And you can see where this is going already. We essentially created PDF files in parallel inside of PLR, right? Which is, again, very, very, very powerful, right? So for each grouping parameter of interest, we were saying, hey, run these routines in R, and then save your visualization, save your plot as a PDF file on a pre-specified file location on each segment, right? And so that's sort of what this PDF function is doing here inside of the function definition. And after we define the function this way, and a lot of what's in here in terms of the code is just kind of specifying how wide do you want your axes to be, what color do you want this line to be, what color do you want that other line to be. So that's standard R code that we're invoking. And then again, kind of the magic happens here when you run the function where you say, hey, run this plot PVA PLR function for each of the grouping parameters that we're interested in, and then store the results as PDF files on each segment. So here's sort of a visual aid that captures sort of what this workflow is doing, right? So again, we have PLR installed on a Greenplum cluster, and in parallel, we're generating these PDF files on each segment in a way that allows you to be really flexible in how you're defining the different plots that are being produced, right? And so not only can you make use of the core plot function in R, but ggplot is another one that you can invoke in the same way. You can now kind of parallelize not only model generation, but visualization generation by using this PLR workflow. So up to this point, we've talked about parallelizing your modeling routines, parallelizing your visualization generation routines. And to really kind of go crazy, what we wanted to do is parallelize algorithmic development using PLR. And so let's say like you love what's in R right now, but you want to like create your own algorithm, I guess computation routine for a new algorithm by using core R functions as your helper functions, right? So let's say there isn't a library in R right now that does this, right? And so one thing that I mean by that is actually being able to do parallel multiple MCMC chains, Markov chain, Monte Carlo chains inside of PLR, right? And so, in the very same way that we've described how to run a linear regression model for each state in your data, what we're doing in this workflow is now running a simulation of a MCMC routine on every single node or segment of Greenplum database, right? And each kind of worker function is invoking the JAGS library inside of R to run those MCMC routines, right? And I'm going to kind of quickly jump through all this because it requires some specialized knowledge on JAGS and bugs in general, which is the code that I'm writing over here. And so what I'm doing is essentially defining the model that I want to run in an MCMC workflow inside of this, let's say, model.bug file. And what I'm doing is I'm now distributing this model.bug file on each segment, so that this information is now contained on each segment of Greenplum database. And in the context of Bayesian regression modeling, one of the things that you'd want to do is increase the robustness of the simulations. And I guess kind of to cut to the chase, the more simulations that you do, the more accurate results generally you'll end up with at the end of the routine. And so typically in this type of workflow, what you'd do is you'd run 1 or 2 MCMC chains on an R laptop, on an R server, and then blend the 2 chain results, and then get to your finalized set of regression coefficient estimates from those 2 chains that you've run inside of your laptop. What the PLR framework on Greenplum allows you to do is run parallel MCMC chains across the entire cluster of Greenplum. So not only are you talking about running 1 or 2 chains of MCMC, but you can run hundreds of chains of MCMC in parallel. And all that we're doing here in this create function statement is invoking that model.bug file inside of this PLR function. And so on each segment of Greenplum, it's going to be replicating this model.bug routine. And again, you end up with sort of each segment on Greenplum generating their own independent set of simulations, which you can then merge back together to get to more accurate results for your Bayesian routine. Now, we've kind of begun to scratch the surface of how you can extend the functionality of existing algorithms in R by using PLR on Greenplum. The next section kind of is, I guess, the last mile, and now what we're doing is we're actually creating scalable versions of existing algorithms by using R helper functions in PLR routines that would define sort of, let's say, a routine for running scalable hierarchical Bayesian modeling models, right? So as it stands right now, there isn't a module, let's say, available in MADlib, in MLlib, in H2O that can run a scalable version of hierarchical Bayesian regression models, right? And so what we've done at Pivotal is actually developed our own scalable prototype for running Bayesian regression by using PLR routines in the back end that essentially compute a lot of the linear algebra computations that are required for something like this, right? And to kind of give you all an overview of, and again, this is kind of getting fairly technical, but to give you all an overview of what a hierarchical or Bayesian linear model is, you essentially have a likelihood function that you can glean from your data. You have what are known as prior distributions for each of the parameters of interest. And so by parameters, we mean things like, we had that regression coefficient for wages and is married in that simple regression example that we talked through earlier, right? So each of these has a prior distribution. And what you do in a Bayesian analysis is essentially get to a posterior distribution for your parameters of interest by estimating the posterior distribution of the parameters of interest by essentially kind of assuming that your likelihood for the, your distribution for the posterior distribution is proportional to the likelihood times the prior distributions of interest. Now that's a lot of mumbo jumbo, I guess, that I've just walked through, but it's relevant in how we talk about the parts of it that are relevant are for how we then come up with a game plan to parallelize this algorithm on Greenplum database using PLR. And so what I've just described in this previous slide is a Gibbs sampling routine tailored for hierarchical Bayesian models. And there are bits and pieces of the Gibbs sampler that can be embarrassingly or data parallelized. And this is precisely parts of the Gibbs sampling routine that we make use of and abuse in certain ways inside of our PLR function for scalable Bayesian hierarchical model estimation, right? So we figure out which components of the Gibbs sampling set of computations that can be embarrassingly parallelized. And then for each of these building blocks, we build a PLR function that corresponds to each of, and essentially it's a bunch of matrix multiplication routines that we can then define in these building block functions. Those are the parts that can be run in parallel inside of Greenplum, which will again increase the scalability of the overall algorithm and increase its performance for estimation. We then build a meta function that kind of ties together each of the functions in two, so the building block functions, to run sort of this meta Gibbs sampling routine inside of Greenplum database. And this meta function is kind of like an orchestration layer almost, where it tells which of these building block functions should be run at which point in time, and then gathers information as needed from the building block functions to aggregate and update the algorithm. And stages kind of 1 through 3 would kind of define one iteration of a Gibbs sampling routine inside of Greenplum. You can then run this function for k iterations and then monitor conversions and then summarize results to produce at the end of your routine. Now, I mentioned building block functions, and here are some examples of what we mean by that. And so one of the building block functions that you'll need in a Gibbs sampling routine for hierarchical Bayesian modeling is to sample from the Wishart distribution. And R conveniently has a function called rwish, which draws random samples from the Wishart distribution. And so that can be parallelized. And because it can be parallelized, we've defined a PLR function, a building block function that serves that purpose, right? Another building block function that we have computed here is the function that will draw new values of beta based on what we've produced in the algorithm thus far. And so again, one of the building block components of a Gibbs sampling routine for hierarchical regression is to be able to take a mean vector from the multivariate normal distribution. Luckily in R, we have a canned function for sampling from, taking random samples, from the multivariate normal distribution, and we make use of it here in this building block function, right? Now in this meta function that we've kind of talked about, sort of this orchestration layer, we put it all together and we package it up. We call it, let's say, a Gibbs init, and we create that function inside of Greenplum, and we specify a set of arguments that each of the different component functions or building block functions will need in their respective steps, right? And I won't go into all the details, but you have an initialization layer that kind of sets the stage and gets the system ready to run your Gibbs sampling routine. And you have a Gibbs update function that says, hey, using what we've just initialized, produce 10,000 iterations of this Gibbs sampling routine, produce 100,000 iterations of this Gibbs sampling routine, and update my results accordingly. And that's sort of what's accomplished by what you see here on this page. So again, we didn't really have a lot of time to go into a lot of the underlying details and how this is achieved, but hopefully this was a way to get you all at least exposed to how you can creatively make use of PLR to build your own scalable versions of existing routines that are out there, let's say as R packages, as Python packages. And before we get to question and answers, I just wanted to close by pointing you to some online references and resources that we have for PLR. So this first link over here is that GitHub Pages link that we looked at earlier on in the session. We focus on procedural language R for today's meetup, but there are also examples in PL Python that you can take a look at on this GitHub page made by one of our colleagues, Ian Houston. There are other ways to make use of machine learning routines on Greenplum database through Madlib and PivotalR and PyMadlib. And we provide links here for those of you who are interested and want to find out more. So thanks again for joining today's meetup. And I guess we'll now go into Q&A.
So one quick one.
Sure.
Can you explain the difference between PLR and PivotalR?
Yeah, so PLR is what we've just talked about for today's session. So it's really about breaking up a problem into chunks and then running each chunk in parallel inside a Greenplum database. PivotalR is a wrapper, an R wrapper to Madlib, which is a machine learning library to run scalable routines inside of Greenplum. And so you can think of PivotalR as kind of, if you're familiar with the Spark ecosystem, it's kind of like SparkR to MLlib or PySpark to MLlib, right? And so it provides, so maybe I should take a step back. So Madlib in its native form provides a SQL interface for canned functions, for SVMs, neural networks, logistic regression, et cetera. If you're a data scientist who is more familiar with R than SQL, then you would access Madlib through the PivotalR layer, which would give you R functions for madlib.lm, which would then invoke SQL routines for linear regression on Madlib in the backend.
So let's say in your example with the 50 states, if I wanted to do one model without grouping it by state.
Yeah. Yep. That would be a better use case for Madlib. Yep. Yeah. Mm-hmm.
Are there any questions from the YouTube?
Nothing from YouTube, but I have one for you. So, in your data science work, especially when you make use of like Greenplum for large data sets, is R the only language you use, or are there other ones you can use?
Oh no, yeah. I mean, R is one of the many languages we make use of. I mean, I guess the other popular one would be Python, and of course SQL. Yep. Those are the three most commonly used by the Pivotal Data Science team.
Can you say a few more words about what is the .bugs file and what is the other thing, the JAGs?
Yeah, for sure. I think we're over here. Yeah. And so the model.bug file, this is something that is an artifact of what, okay, so maybe to take a step back, we should describe what JAGs is, right? And so JAGs is, actually, why don't we go to the page for JAGs on Google here. So JAGs is short for just another GIP sampler, and it is a computational library that allows you to run Bayesian GIP sampling routines on platforms like R, right? And so in R, you'd have a connector to the JAGs computation engine called RJAGs, which would invoke JAGs sort of in the back end, right? One of the things that you would be required to do or recommended to do in a JAGs routine is to produce a model.bug file that describes what you want to do in the GIP sampler. And so this is typically supplied as a text file that looks a lot like this. This is just one example. And so this specifies, we talked about the prior distributions, the likelihood functions in one of the previous slides. And so that kind of defines the specific instances of the prior distribution, let's say, that we'd want to incorporate for this analysis. And so this text file is then kind of sent to all segments of Greenplum database. And then when you create a PLR function that calls the JAGs library, the RJAGs library, as we're doing here, RJAGs needs to find a model.bug file. And so this path is kind of how we're invoking and allowing this PLR function to find that model.bug file for use in analysis.
And what type of business problems are well suited to Bayesian hierarchical model as opposed to linear regression? Like when would you use Bayesian hierarchical model?
I'd say whenever you can. Yeah, in many cases, it's the better alternative compared to vanilla linear regression. But it's especially relevant in situations where you know you have deficient data. So you could run a linear regression model on some data, but if you are not sure whether that data is of high quality, then you're better off running a Bayesian hierarchical linear regression model. What that is essentially kind of conceptually, let's say you want to estimate the impact of price on sales for Coca-Cola, let's say, right? And you have some data on prices that were charged for Coca-Cola, and you have corresponding sales metrics for Coca-Cola, let's say by state, right? And the problem here, though, is that let's say you only have a few data points for California, and you only have a few data points, let's say, for New York, right? And you have a few data points, and this is happening in all the states. So for each of the 50 states, you have like a deficient data set, and you get kind of results that are kind of all over the place in the context of estimating the impact of price on sales for Coke, right? Here's one way where you can kind of, judge that or test that. If we're estimating the impact of price on sales, we would probably expect to see a negative impact of price on sales, right? So as you increase prices, sales will decrease, right? And so that is represented by a negative coefficient in the context of regression, right? But as any practicing data scientist knows, you often get coefficients that are just all over the place. You get positive price coefficients, which doesn't make a lot of sense. So it's basically saying if you increase prices, you'll increase sales, right? And so that often happens when you have deficient data sets. One of the solutions to address that challenge is, let's say, a Bayesian hierarchical linear regression model, because if, in one scenario, let's say you have, of the 50 states you've run regressions for, let's say 80% of those states, well, let's just say 30 of those states have negative price coefficients, but 20 of them have positive price coefficients. And you're not going to go back to the client and say, hey, you can increase prices in these 20 states and just continue to increase your revenue. That doesn't make any sense, right? What that probably means is that the data for those 20 states are deficient, right? And what you do is essentially learn from the experience of other states. So that let's say if New York is one of the 20 states that has that funny price coefficient, you can average, in a sense, average the price coefficient for New York, which is positive, with the price coefficient for all of the US, a national model, which takes into account the data from all 50 states, which we're assuming here is a negative value, right? So if your coefficient for New York was slightly positive, if you average that, weighted average it with the national coefficient for price, which is negative, it's going to steer it over to kind of that negative value, the value that makes more sense, right? And so you're kind of getting it to, again, kind of learning from the experience of others and partially pooling the results of the price coefficient from different states for New York. So this is one of many use cases in which you'd want to use something like hierarchical modeling. It's in many ways similar to what Nate Silver uses in his pooling result aggregation algorithm, where he's weighing and kind of assigning weight to each poll that he gets election predictions for. And if it's like an internet poll, then you're going to assign that smaller weight. If it's a more trusted poll, you'll have it assigned a more stronger weight. Then you average the results from all those different polls to get to a more reasonable result.
Is that why it's called hierarchical?
Yeah, exactly. You're kind of invoking this hierarchy on the data where you have states, which kind of roll up to the US national model. And you can take it a step further and go worldwide, where you can then partially pool across countries of price coefficients.
I have a couple of online questions if we're...
Yeah, for sure.
So first one is a technical one. Brandon online says, as far as he understands, GPDB, so Greenplum database array, has a 1 gigabyte limit. Yep. Does this limit how you can use PLR and PLPython?
Yeah, that's a really good question. Yes, if you array ag it, then it will have a 1 gigabyte limit in terms of the data that you can store in that one record. But then we didn't go into details of the approach in this session, but there's a way to get around that by using SQL aggregates instead of array ags, which will expand the memory limitations to only be limited by what's available at the segment level on Greenplum.
And Brandon has an additional question here, so if I can get it all in here. Our team has tried to use ready-made R packages in PLR, but we find that most packages accept matrix, data frame, or list. We need to convert multiple rows to array to hit the limit easy.
Okay.
Maybe referring to the prior.
Yeah, it may be the prior question. And so if you are running into
So he actually qualified his question in the line below. Sorry about that.
no, that's okay. Yeah.
What is your suggestion for using ready-made R packages with PLR?
Use them whenever you can. Yeah, I mean, that's the whole point of using PLR, is the fact that you can import these libraries at will.
So do we have a reference online for using ArrayX to summarize the data rather than ArrayX?
Using aggregates, you mean? Yeah. Yeah, there is a reference page. Let's see here. I think it's something that Watson may have.
Yeah.
And you actually, Ivan, may have authored, right? So I think it was for PL Python. Yeah, here we go. Yeah. So yeah, I think this is the right page. Yeah, here we go. Yeah. So we can point you to this page over here. It's on the Engineering Pivotal blog. This is something that Ivan and Watson, one of our former colleagues, had put together. It defines and gives you some examples on how you use SQL aggregates instead of array ags for your PLX workflows. They focus on PL Python in this example, but you can apply the same principles for PLR and PL Java if you're interested.
Any more questions from the audience?
No more questions online at this time.
Okay. Well, thank you very much.
No worries. This was fun.